Okay, don't be shy participating. Even if it's recorded, I cannot see your face anyway. Matrix is an arrangement of numbers. These numbers provide some information. For example, when you take a photo, a picture, the pixels of that picture are stored in matrices. You don't know it, but there are matrices there with a huge amount of rows and huge amount of columns. This matrix has 2 rows and 3 columns. 1 row, 2 rows, 3 columns, 1, 2, 3. We can do operation with matrices. For example, we can add 2 matrices. Only the matrices have the same dimension. They can be added. I can add these 2 matrices because they have the same size. 2 by 2, 2 by 2. How do you add the matrices? You add each element. 3 plus 4, 7. A plus 0, A. 4 plus 1, 5. 6 minus 9, minus 3. I listen some mouses like. But anyway, I will try to talk louder. Okay. Then, of course, at the end, the final matrix has the same dimensionality as the original. You can create the negative of matrix. You can multiply by minus all the matrix, and then you have to multiply by minus all the elements. Minus 2, minus plus 4, minus 7, minus 10. You can subtract 2 matrices in the same way. You subtract element by element. 3 minus 4, minus 1. A minus 0, A. 4 minus 1, 3. 6 minus 9 is 6 plus 9. It's 15. You can multiply a matrix by a constant. 2 times this matrix, you have to multiply each element by 2. A 0, 2 minus 18. Scalar multiplication. For dividing a matrix, you cannot divide like this in the sense. You have to find the inverse. So I will show you here on the board that when you have a matrix, you have a matrix A. Let's assume it's 3, 2, 1, 0. It's 2 by 2. And I want to divide this matrix by this second matrix. I cannot divide directly. What I do is I find the inverse of this matrix. I have to calculate the inverse of this matrix because the inverse of a matrix is a matrix such that when I multiply the matrix by the inverse, I obtain the identity matrix. What is the identity matrix? It's a matrix with ones in the diagonal and zeros in the non-diagonal terms. And any matrix multiplied by the identity gives you the same matrix. This matrix is equivalent to the number 1 in the numbers. It's a multiplying by 1, and the number gives you the same number. If you multiply any matrix by the identity, you obtain the same matrix. Okay? So it's more or less. Why this is useful? Because sometimes you want to store the data in matrices, and then you don't want to manipulate equation by equation. You want to manipulate the whole block immediately. Then if you know the operations, the matrix operations, you can just manipulate the whole data directly without worrying so much about each one of the equations. And of course, at the end, you will put this in a software. The software will calculate the inverse. The software will calculate things, but at least by knowing basic cases, you will know what you are doing. I mean, you need to know what you are doing. It's not only put things in the software and getting things. You need to know more or less what is the concept behind that. Coffee. Nice. Okay. So when you divide the matrix, find matrix U, you have to find inverse. There is no division in the rigorous sense. The transpose of a matrix is an operation. You have this matrix and you apply the transpose, then you obtain this matrix. You will analyze 6, 4, 24 now became column. And 1 minus 9a became column here. So this operation is called transpose. Sometimes some matrices are special and they are their own transpose, etc. This is the usual notation people use for identifying the numbers. The first element is the 1, 1 element. The second element here is the 1, 2, 1, 3, 1, 4, blah, 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 blah. If you have more. And for the second row, all the first numbers are 2. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. And if there is a third row, it will be 3, 1, 3, 2, 3, 3, 3, 4, blah, blah, blah. Yeah? It's just notation. Because you can talk to your friends, the element 1, 1 is that. You need to give the coordinates of the element. So, for example, in this matrix B, the element 1, 1 is 6. The element 1, 3 is 24. 1, 1, 1, 2, 1, 3. The element 2, 3 is 2, 1, 2, 2, 2, 3. 8. Okay? So this is simple notation. Anything to ask here? Any question? Is very clear, right? Very easy for you guys. For who is difficult? Somebody find it difficult? I mean, I know some of you guys are in humanities or so. Well, of course, unfortunately, the course is quantitative there. You need to. And in humanities, you can use these things. You can use it. It depends how deep you want to go or how much you want to quantify your research. Now, if you only want to do pure history or pure things and without numbers, that's up to you. But of course, these tools, you know about the existence and about the possibility to use them anytime. Now let's go to multiplication matrices. Because matrices not only sum, divide, they also multiply. So now let me go to here to see if I am sharing the right screen. Yeah, I am sharing the wrong screen. So now here. How to multiply matrices? Well, when you multiply scalar, it's trivial, no? I explained that if you multiply a number by a matrix, you multiply each element. 2 times 4a, 2 times 0, 0, 2 times 1, 2, 2 times minus 9, minus 18. No problem. But what about multiplying two matrices? This is what we call dot product in linear algebra when you multiply two vectors. A matrix is an arrangement of vectors. It's like putting a bunch of vectors in a single mathematical object because each column or each row can be seen as a vector with the components, no? The corresponding components. Of course, you can also see it as a linear equation. I will show you later how to see it. You can arrange equations in matrices. You can arrange data in matrices. You can do many things with matrices. And it will facilitate your life. Because if you create a matrix and you do it the whole time, I'm sure you have done it and you don't realize. When you put in Excel the values in column in the cells and you multiply things and you are doing this exactly this thing we are explaining right now. That's what you are doing. It will come later, some examples. Some examples are going real life examples. You can use, for example, for the inventory in a supermarket, for knowing how many products you sell, many other situations. And engineering, people use it for calculating the principal axis where the system, or for example, a bridge, the columns of a bridge will suffer the biggest deflection This can be done with linear algebra and doing something called eigenvalues and eigenvectors, which we will explain later. Eigenvalues and eigenvectors, which is very important, will tell you how to locate the principal axis of any data. And when you locate the principal axis, that's important because the data is symmetric with respect to those axes. You can find some axes. For example, you have X and Y, no? But you want to find the axis with respect to which the data is symmetric. And that's found by some methods, which I will explain later. And also some software give you these values. They give you the eigenvectors, they give you the eigenvalues. So this is a dot product. Between matrices, you multiply each row with the corresponding column. 1 times 7 plus 2 times 9 plus 3 times 11. They give you this number. Then after you take this first row with the second column, 1 times 8, 2 times 10, 3 times 12, and this is the number here. And so with this column, you repeat the same operations and you obtain this and this number. At the end, the first matrix is 2 by 3, and the other is 3 by 2. You have one matrix, 2 columns, 2 rows, 3 columns, multiplied by a matrix, 3 columns, 3 rows, 2 columns. When you multiply these two, the final size of the matrix, it will be 2 by 2. No? So for the multiplication of matrices to be possible, the number of columns of the first matrix has to match with the number of rows of the second matrix. So you cannot multiply a matrix. If you add one more, what happened? Oh, I didn't do anything. Okay. It seems that the system is afraid when I do it. No. Or maybe some vibration. Exactly. If I add one more column here, I cannot multiply these two matrices. If I add one more row here, yeah, I could technically. No, I cannot neither. So the point is that the number of columns of this matrix have to match with the number of rows of the second. If these two numbers don't match, 1, 2, 3, okay. 1, 2, 1, 2, 3, 1, 2, 3. The number of columns here has to match with the number of rows of the second. If these numbers don't match, let's say 1, 2, 3, if I add one more here, then I cannot multiply these two numbers. And you don't have to worry about how to multiply matrices in detail because I can do it in the software I showed you yesterday. And let's show you immediately for you to realize that it's not that difficult. Because this is, when you're doing research, there is something when you're doing research. You are getting weapons. It's like a video game. Do you play video games? I don't play, but I have seen that in some video games, you advance, you get more guns, more weapons, you become stronger. Well, this is research also. The more you learn, the more weapons you have, the more things you can do. So it's up to you how much you want to learn. But the more you do, your thesis will be better, I think. That's a fact. Then let me open this guy here. Sign in. I think I logged out yesterday for any reason. Remember me. Okay. Never. I will bring this here. This guy here. I will write this matrix. Let's write this matrix here. The matrices. The first one is 1, 2, 3, 4, 5, 6. And the second is 7, 8, 9, 10, 11, 12. And I want to multiply this. Of course, what I do is this times this times this times this, give me this number. Here's this with this, no? And then after this, with this second column, and I obtain this number. And I continue with this, with the first column here. I obtain this number, and this with this column here, I obtain this number. But when you are in a software, you don't have to do so much. What you do is, let's put it here. You go here. Well, let me see that I am sharing again the appropriate. Yeah. You go here and you put matrix. I can put better matrix. Well, matrix multiplication. Linear algebra, well, I will put matrix operations better. But after I know how to do it, but I just want to copy paste something here. Product of matrices with the dot here. Okay. Something like this. I will copy this one. I will paste here. I will omit this thing. Then the matrix, the first matrix, which is 1, 2, 3, I will put here 1, 2, 3, 4, 5, 6. And the second matrix is 7, 8, 9, 10, 11, 12. If my memory is right, this should be okay. So evaluation cells. This is the final result. And now I want to show let's put it in matrix form maybe. Well, this guy doesn't allow me to do it. Evaluation cells. Most element. I can calculate actually transpose if I want any operation. Look at the transpose of this. Well, let me write it in a more friendly way. I will copy and paste here. Here. Down, down. Well, this is the matrix notation of this. But actually, I already did the transpose. It's doing the transpose. I didn't want to make the transpose. Well, anyway, the point is that final result is not right because it did the transpose. I will show you what the system did. What we did is the following. We multiply those two matrices. The matrix 1, 2, 3, 4, 5, 6 is multiplied by 7, 8, 9, 10, 11, 12. And that gives you the result is 58, 64, 139, 154. And then the system calculated transpose of that and give you 58, 64. If I calculate 139, 154. Correct? Ah, no, yeah, that is correct. Yeah, sorry, I was reading it wrong. This matrix is equivalent. So what the system order is actually, sorry, is here. Let me put here 139, 64, and 154. So I mean, this is the first holding. What happened? I stand. Okay. This is the first row, and this is the second one. Okay. But since I get the order of transpose at the end, this guy gave me the transpose in May. The transpose is the 159 will appear here and the 154. But what you have to understand right now is that there is an easy way to calculate the product of matrices. Even if I put the sum of matrices, for example, I want to sum two matrices, sum matrix operations. Let's put this operations. What I want to do in another chart better, because I want to close this one. I want to close this one, and instead I want to use a new one. Why I do that? Because sometimes if I am not careful, the system store previous orders, and then it will continue recurrently executing those orders. So sometimes I prefer to start with a new notebook. Then, for example, matrix operations here. I can do these matrix operations here. I can calculate the inverse of a matrix, for example. The matrix rank, the transpose. I can calculate the diagonal matrix. I can calculate the trace, the determinant. The trace of a matrix is the sum of the diagonal terms. When you sum the diagonal terms of a matrix, that's the trace. For example, and it has to be a square matrix. Let's put it this way. Well, this matrix, the trace is 58 plus 140, 54, for example. That's the trace of a matrix. If I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and I calculate the trace of this, what is the trace of this matrix? Who can tell me? Sum of diagonals, 1 plus 5 plus 9, 15. Right? Okay, this is the trace of this matrix. Okay? The determinant of the matrix is a different operation. And let's check if we can really calculate the trace here. Let's go here. Trace, for you to trust, well, what? They write in this way, but I don't like to write in that way because it looks, I will write the matrix as we know. It's like this, 3 columns, no? Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 15, right? This is the trace of this matrix. So, I mean, at the end of the day, when you have a huge matrix, you just put here and the system will calculate for you. Because, of course, now we are seeing only the trivial cases, no? Trivial cases. But in your research, probably you deal with huge amount of data, a lot of dimensions in your data. Then I think matrices is the best for storing this information. So let's go back to matrix multiplication, or to multiply matrices. these operations. I want to see if I am sharing the right screen. Here. So this is the multiplication matrix with another. I can also, so at the end, these are the numbers you saw, 58, 64, blah, blah, blah. It finished being like that. These are the numbers we saw in the when we developed the product. Now, this is an example. This is what somebody was asking me, real case applications. How do you apply this? The local shop sells 3 types of pies or whatever, bananas, I don't know, chocolates, strawberries, apple pies, $3 each, cherry pies, $4 each, blueberry pies, $2 each. And this is how many they sold in 4 days: Monday, Tuesday, Wednesday, Thursday. 星期一、星期二、星期三、星期四. Right? Right. So apple, I don't know how to say apple in Chinese, sorry. Cherry and blueberry. And on Monday, they sold 13 apples. On Tuesday, 9 apples, 7 and 15 on the other days. Cherry, 8 on Monday, 7 on Tuesday, 4 on Wednesday, 6 on Thursday. Blueberry, 6 on Monday, 4 on Tuesday, 6 on Wednesday, 3 on Thursday. So, the sellings. Think for a moment, how do you calculate the sellings then? In money. Obviously, the number multiplied by the price, but how do you do that in matrix notation? $3 is the apple, $4 is the cherry, and $2 is the pies, right? The blueberry. Everything is pie, actually. The blueberries. And this is the 13A6 for the first column, which correspond to apple, cherry, and pie. This is just for the first day, Monday. You obtain $83 in sellings. And then you repeat the same operations with the other days, Tuesday, Wednesday, Thursday. In matrix notation, it's like this: $3 for the first product, $4 for the second, $2 for the third. And these are the sellings for the corresponding days for each product. Apple, I forgot the other, and blueberry. Let me see. Cherry and blueberry. Apple, cherry, blueberry. Okay. Apple, cherry, blueberry. The prices correspondingly. Then this is the operation, the compact way to do this operation. For Monday, Tuesday, Wednesday, Thursday, and then you obtain the totals for each day for Monday, Tuesday, Wednesday, Thursday. So you roll something which you could calculate, no, but it's easy. But what happens if you have a huge amount, you have 7 days, and you have a huge amount of products? You will do it one by one. No. You will collect them in a matrix, and then you will put in the software, and the software will give you the total sellings of each product immediately. So, I mean, if you write, there are many different ways to write data. Somebody can tell you data, and you can have many different ways to process it, many different ways to store it, different ways to display it. But the more compact you are, and the more concise, and the clearer, and the most simplified version is usually the best. And the most simplified version is this. And of course, this demands you to have some knowledge in linear algebra. Linear algebra is underestimated in some universities. but I don't blame. Some universities start with, when the universities start with humanities, is normal. But linear algebra is the most important subject somebody can study in their life. It has plenty of applications. In quantum mechanics is formulated with linear algebra, basically. Let's start from that. Business, finance, game theory, decision theories, these kind of things. Even the pictures, you like to take pictures. The guys who could design these things, the pixels are displaying matrices, huge matrices. Actually. If you see the information of a picture, you will see a matrix. Huge matrix, the pixels. So, I mean, it has plenty of applications. And of course, those guys who do machine learning seriously, because it's true that some guys say, I know AI, but no, knowing AI is not knowing ChatGPT, yeah? Because some people appear like, I know AI, I'm an expert in AI. What do you do, ChatGPT? Come on. I mean, knowing AI is doing machine learning from zero and really displaying, really programming, really developing the algorithms and so on. That's knowing AI. If you don't do that, you don't know AI. What you do is you know how to use AI. It's different. Knowing how to use AI is different to knowing AI. Then it's two different things. Well, the point is that I am not claiming that you have to be experts in these kind of things. What I claim is that you need to know the existence of these things. And if one day you need it, because I mean, the clever person is not the person. This is a saying. No? Some people say the clever person is not the person who knows everything, but knows in which moment has to learn the things. No, and in some moments, when you need to learn something, you will do it if you need it. Then you know that this exists. What is the most compact way to store information? Matrices. Okay. I will try to put, and it looks very elegant. Imagine a thesis, you display your matrix, blah, blah, very compact. People read it and they will say, yeah, that. Actually, if the appropriate reader comes, because it's not necessarily true that some professors really know that because their fields, their expertise might be different. Anyway, look at this. The matrix operation product 3 times 13, 4 times 8, 2 times 6 gives you the first number, and so on and so on. This is a vector. Actually, this is a vector of prices. One column or one row matrix is a vector. It's a vector of prices for the pies. $3, $4, $2. You study vectors in the high school, no? Vectors. When you study a vector can have how many components? As many components as you will. It could be infinite dimensional if you want. Well, when you portray in your Euclidean geometry, you have 3 dimensions, no? In this case, by chance, there are 3. One component is 3. Second component, third component. This is another way to represent the vector. Let's call it vector of prices. 3, 4, 2. In components, 3, 4, 2. If you display in a 3D diagram, 1, 2, 3, 1, 2, 3, 4, 1, 2. This is your vector of prices. So one column or one row matrix is a vector. And a matrix is a bunch of vectors. We have 1, 2, 3, 4 vectors, each vector corresponding to each day. And what you're doing here is a dot product, a basic operation you should have learned in school actually. Dot product between this vector and the first, this vector and the second, this vector and the third, this vector and the fourth. And that's it. Since this is a 1 times 3 matrix, multiplying 1 times 3 matrix, 1 row, 3 columns, is multiplying at 3 rows, 4 columns. Then these two guys disappear. They are dummy index, and at the end you obtain a 1 times 4 matrix, which is what happened here. Is one row, 4 columns. Of course, these things I can see it easily because for my expertise, but I am not pretending you to see it so quickly, but you should know that there are simplified ways to perceive this. For the moment, what is important is that you can develop real cases with this. And then, of course, for your final presentation, if somebody can really display all the skills, that's a sure 20, secure 20 in the class. You can multiply 2 vectors in this way. This is the multiplication of 2 vectors gives you a number, actually. This is just the standard. The standard multiplication of 2 vectors number. 2 vectors number. The identity matrix is what I was telling you before. Identity matrix is a matrix. It's a square. This is a 3 times 3 because it's 3 columns, 1, 2, 3, and 3 rows. Or 3 rows, 3 columns. The diagonal is 1. The non-diagonals are zeros. If you multiply any matrix by the identity, you obtain the same matrix. So the matrix, the identity matrix is equivalent to the number 1, like the unity in the world of matrices. You multiply any matrix, you multiply any number by 1, what do you get? The same number. A times 1 is A. 2 times 1 is 2. When you are learning as a kid the multiplication table, that's the easiest one. No? And the 0. Multiply by 0, multiply by 1, and multiply by 10. Those are the easiest, no? Because normally they teach until 10 first, and then after, if somebody wants to learn higher, it's okay. All the others are memorized. Now, then somebody can ask why we need to learn this, why we don't jump directly to the grain, and so on. This desperate strategy, which is becoming a disease in the new generations, is not right, because everything is a process. Learning is a process. The difference between guys who can do good research and guys who cannot, or guys who can remember things and guys who cannot, is that those guys who can remember things and can do the things very well, they don't make shortcuts. They really learn the things process step by step by step. Then wonder you serve, imagine a kid saying, no teacher, I don't want to learn multiplication because I want to go to the grain immediately. What would you tell to that kid? You will tell him something, no? The same happens here. So these things are necessary if you want to be quantitative. Now, some of you say, no, I don't need this. My supervisor doesn't want me to use this. That's up to your supervisor. But my mission here is to give you the tools. Now, you take it or leave it. Well, the course is quantitative, no? Then that's my mission here. Order of the multiplication matters in matrices. When you multiply numbers, the multiplication is commutative. What does it mean? It means that 3 times 5 is the same as 5 times 3, right? In matrices, no. If I have a matrix B A and I multiply by a matrix B, it's not necessarily true that B times A is the same. So the order of multiplication matters in the matrix world. We call it non-commutativity of the product of the matrices. So in high-level maths, we know that not everything commutes, especially those who know quantum world, quantum mechanics, and so on. We find these situations many times. There are many operators that don't commute. By the way, the course I am offering quantum communications and technology, it will not have so much math, so don't worry if you are going to register. It will be more concepts. It's a divulgative, any audience. It's different to a rigorous course. No? So let's do an example of a matrices. These two matrices, imagine, they have the same dimensionality. 1, 2, 3, 4, multiply 2, 0, 1, 2. When they multiply, they obtain this. But when you reverse the order, you obtain this completely different result. Completely different. So the order matters. And you know, this is the biggest error of many bachelor students when they are doing matrices. Because actually in FBL, Faculty of Business and Law, I used to teach calculus, no? When they have calculus. Now they don't have it. Calculus 2. In calculus 2, I was teaching a little bit of linear algebra, these matrices. And some guys commit this mistake. They didn't care the order. For dividing the matrices, they do whatever. No, you cannot divide matrices. You can find the inverse of one matrix, and when you multiply one matrix, but that for the inverse of the other is equivalent to dividing them. In other words, if you have an equation, let's put it in the board here, for you to understand what I'm talking about. In numbers, this is correct. In matrices, in some cases it's true. There are cases where A, B is equal to A. I will give you one simple case, the identity. If you multiply this by the identity, is equivalent to identity times A, it gives you A. This is one case, the trivial. The identity is the unit. And there are other cases, there are some matrices which commute, but those are special cases. In general, it's not like that. And I say something else. I forgot what else I said. What is the other thing I said? I talk about the order of multiplication and division. Division. If you have an equation, when you have one equation, for example, x equal 3yc, you obtain this relation between variables, and you say I will divide x by y, and this is 3c. This is division, no? You divide it by y. You cannot do that in matrices. In matrices, let's assume that X is a matrix. Let's put the matrix like that with a hat. Let's assume that Y is a matrix and C is another matrix. In matrices, if I want to divide, first I have to multiply on the right by the inverse of C. Then I will multiply here the inverse of C here. And then a matrix with the inverse, the product will give you the identity. And then after I have to multiply again by the inverse of y. And this is another identity. And then at the end, this is equal to 3. Then now it's true. I solve 3. Or if I want to leave the y here until this point, okay. It's okay also. This is the way to divide matrices. This inverse is an operation. It has to be done seriously. In the case of 2 by 2 matrices, it's trivial. But when the matrices are larger and larger, it's more difficult. Then you use the software. In 2 by 2 matrices, it's very easy. Everybody knows that. Not everybody knows. Let's put everybody who knows math. They know that you have a matrix A, B, C, D. A, this matrix A, the inverse is 1 divided in the determinant of the matrix. D, A minus B minus C. I think it's like that. And the determinant of the matrix is A D minus CP. This is trivial in that case, but for larger matrices, then you use what? The tool I showed you now. We will learn how to make these operations. There is one session exclusively, I think it's next Friday, actually. It should be next Friday. I will check the calendar. Because next week, Wednesday, I think we will see hypotheses and these kind of things for complementing the statistical part for collection of data. And then after, we will have one session where we will do regressions, this, blah, blah, with software for you to have that tool. Free resources. I am friend of the free resources. I don't put my students to pay things. I don't like that idea. Well, some people don't care. If you have excessive money and you want to pay, go ahead, man. Well, I try to help you to save, no? It's my purpose, at least. No one of my students pay a single cent doing their thesis, actually, when they're working with me. Not even for the publication, because we don't pay APCs. Then, well, I know some, it's not bad anyway. Some professors, they need to pay. It's okay if they have the money. Or some people pay for attending conferences. I don't do it. I go, in my field at least, most of the conferences are free of charge. And it's the other way around. Sometimes they pay you to go. Then it's more or less like that. Now we are in this part of non-commutative. It's still 8 p.m. We have 30 minutes. Wow, this is really, the time is really going well. Now we know how to multiply matrices. Now let's go to another operations. Other operations. Where is the mouse? Here. I will close this one. And I will close this one. I will bring, well, I will bring one screen here. Before the determinant, I will teach you how to calculate the inverse of the matrix. This is what I was talking about just a few seconds ago. Inverse of a matrix. And let me share the screen here. The inverse of 8, for example, you have a number, and I want to tell you what is the inverse of number 8. It's 1 divided 8. Why? Because when you multiply a by this number, you obtain 1. So it's equivalent to find the inverse of the number. No? The reciprocal of a is 1 over 8. In matrices, it's the same. The inverse of the matrix is represented with a -1 here. And we don't use this notation because there is no division in matrices. You can calculate the inverse of the matrix. Then in the same way as A multiplied by the inverse is the reciprocal is 1, a matrix multiplied by the inverse gives you the identity. Remember, the identity is one matrix with all the elements diagonal 1 and outside diagonal 0. Okay? Something happened. This should work. Yeah, it worked. Let's put it like this. Identity. I will not specify the dimensions, but it's a matrix with 1, 1, 1. As many ones as many dimensions you want to include. And this is 0, 0, 0. All these 0, all these 0, all the elements in this 0. This is an identity matrix. It's equivalent to the model 1 in the multiplication of matrices. Right? This is the identity matrix for a 3 by 3 matrix. only three columns, 3 rows. Take into account that the identity matrix is a square matrix. Same columns, same rows. I mean, the same number of columns as rows. And when you multiply matrices, they don't have to be the same size, but at least the number of rows of one matrix has to be equal to the number of columns of the second matrix for the multiplication to be possible. Some matrices cannot be multiplied. There are matrices, there are cases, there are even worse cases. There are cases where you can multiply the matrix in one direction but not in the other. There are cases where A times B is defined, or B times A is not defined. Not possible. There are cases where you can multiply the matrices in one direction but not in the opposite direction. Due to the non-commutative rule, anyway. But in some cases you can do it, but in general the result is different. Okay? In 2 by 2 matrix, I think I showed this before. In 2 by 2, everybody knows the formula. Just change these two numbers, D and A, and you put minus here and you calculate the determinant. Later you will learn that this operation below is the determinant of a matrix. And this tells you something. The matrix only has inverse if its determinant is different from 0. This is a rule. These are rules. If a matrix has a 0 determinant, you will learn now what is a determinant. Determinant is an operation. It's equivalent to the magnitude of the matrix. You have the magnitude of a vector, which is the length of the vector. The matrices also have some magnitude, some number associated to them. And that number is called determinant. There are matrices which denote operations of rotation over a vector. The determinant of those matrices is 1. I will show you more. For example, some vectors, let's put like this. You have a vector here, and you want to rotate the vector here. Angle, some angle. This operation is done via matrices. You have a matrix here. I forgot the other way, it's cosine, sine, something like that. And you have the vector here, A, B. This is the vector. This gives you A prime, B prime. This matrix for generating only rotations has determinant equal 1. So whenever the determinant of a matrix is equal to 1, it doesn't change the length of the vector over which it operates. These are rules. I am just mentioning this rule for completeness, but in most of the cases, it will not be your business. Let's say you will not care this too much at the moment of doing the operation. But I suggest you, if you are dealing with matrices, and in your thesis there is a moment where you deal with matrices, and your supervisor is not expert in math or something, I suggest you to support yourself to consult to some expert in math, at least. Friend, whatever, or professor, whatever, doesn't matter. You can ask, because there are some tricks which facilitate the calculations. No? There are some tricks. So anyway, you can calculate the inverse of the matrix. The inverse of this matrix, for example, is this value. And you can, I guarantee you that if you multiply the original matrix by the inverse, you obtain the identity. Let's actually we can certainly do it. We will do it later. We will do some exercises later and you'll be convinced about that. Then applications of the inverse. Sometimes you have an equation like this, matrix equations. X times A. X is a matrix. A could be a matrix, a vector, or a vector, whatever. And B is a matrix or a vector. Then you want to solve, let's assume you want to solve X here. How do you solve X? You will not tell me, you will divide by A here. You will You move this A here, multiply to divide here. No. You have to multiply by the inverse of A on the right-hand side here, and by the inverse of A in the left-hand side, in this side here, the right-hand side or the left-hand side. And A times the inverse is the identity. And then you have solved, because X times the identities is the same matrix, then you have solved X. And now let's go to a real life example. Bus and train. A group took a trip on bus at $3 per child and $3.20 per adult for a total of blah, blah, blah. They took the train back at $3 blah, blah, per child and $3.60 per adult for a total of how many children and how many adults. Okay. Then you can create this product of matrices. By bus, it was $3 per child, 3.20 per adult. So this is child adult. Each row has a label, child adult. For coming back, 3.5 per child, 3.6 per adult. So the first row is child, the second column is adult. And then you multiply on the left by two variables, number of childs, number of adults. This is a vector. And this is a matrix multiplication. And you know that the total they spent by bus is 118.4, and what they spent by train is 135.2. And then when you multiply this, the rules say the first element times 3 plus the second element times 3.2. This is the first equation. Will be equal to the first number. And the same, you repeat 3.5 times x1 plus 3.6 times x2 equal 130. And if you don't know, you forgot how to make this operation, you put in the software, this product. And the software do for you. And then equal to this, solve the equation. And then at the end, you have, when you solve x1, you have 16 children, 22 grown-ups. So, I mean, the point is that you can simplify the way how you display equations by using matrices and linear algebra. And this extended, of course, this is easy. There are only two labels, grown-up and child. But what happens if you want to classify by race, Western, black, white, whatever, Asian, I don't know. Or you want to classify by ages, by different ages, 1 to 10. Well, the babies should be free, maybe. 10 to 20, 20 to 30. I mean, it depends how many levels you want to classify. The number of levels, the number of rows will increase. You will have more rows. And then when you have a huge amount of rows, this kind of operations will be a bless for you. It will facilitate your life. This is another way to, I mean, you saw one example where they wanted to solve the first variable, no? Here. I wanted to solve x, but x was on the left. Now what happens if x is not on the left, but on the right? Then in this case, I have to multiply on the left for the inverse here in this part. For obtaining the identity here, this is what they do here. Consistently, I have to multiply on the left also, the inverse of the matrix and here. And then you obtain this. The identity times x is x. And then you can solve the equation. Okay? So these are other examples, blah, blah. Sometimes the inverse doesn't exist. Why? When the determinant is 0. Those matrices we call singular. When the determinant doesn't exist, you cannot find the inverse of the matrix. It means there is no matrix such that multiplying the original matrix, you get the identity. In such cases, we say this matrix is not invertible and the determinant is 0. That happens in some cases, and it could happen when you have redundant columns or redundant rows. For example, you can have a matrix like this: 1, 4, 5, 3, 2, 1, 1, 4, 5. These two guys represent the same. The determinant of this matrix is 0. I know by hand because they are repeating two rows. If you repeat 2 rows or 2 columns, or you can simplify 1 row and demonstrate that it's equivalent, that 2 rows are equivalent, they can represent the same number. For example, if I multiply by 3, this one, 3, 12, 15. Still, these two rows are equivalent because I can reduce by operations this to this. In such a case, the determinant of this matrix is 0. In these cases, also if I repeat columns, let's put here 20 for changing. If I repeat, for example, 1, 3, 3, and I put here 1, 3, 3, also determinant 0 for this. So in some cases, it's not that easy to see if there are redundant columns, redundant rows. Then you calculate the determinant. Determinant gives 0. It means that at least 2 rows or 2 columns can be simplified to be equivalent. That's the meaning of that. You have some redundancy in your system. Redundancy. You have more equations than variables in such a case. Those matrices are not invertible. You cannot find inverse of that matrix. But precisely the 0 determinant condition is what helped me to find the eigenvalues and eigenvectors, as I will display you later. In other words, let's simplify the thing. If I have an equation A, X, A equals C, and I want to solve X, if this matrix has no inverse, non-invertible matrix, then you cannot solve this. There is no way to do it. And when does it happen? If I calculate the determinant of A and I get 0, there is no inverse of A. This doesn't exist. However, if the determinant is different from 0, then I have this, and then I can solve it, because then I can say X, A to the minus 1 equals C, A to the minus 1, and this is my identity. Well, X times the identity is X, so I solve X. Matrix, these are matrices. So X, what I mean is that X itself is an array of numbers. And C also, and A also. Could be vectors, could be matrix, could be anything. Okay, now we are moving quite fast in this. I will display now how to solve systems of linear equations using matrices. Because sometimes you have equations in your analysis. You have equations, a set of equations, and you can display those set of equations in matrices. For example, these equations, you have one equation, 3 variables. Let's say you did an experiment and you found some relations, potential relations between variables in this way from 3 equations. X plus Y plus C equals 6. This is a plane, the equation of a plane in 3D. 2Y plus 5C. This is a straight line in the plane, in the projection YC. And this is another plane also. Plane of flat surface, because there is no quadratic term here. Then you can put this in matrix notation, actually. How do you do that? in matrix form, look at this here. Let's put here. Well, this is not this. Let's put like this. This is the first equation. This is the second equation. This is the third equation. I could arrange like this. 1, the first coefficient of the first equation is 1. The coefficient of the first variable. The coefficient of the second variable is 1, and the coefficient of the third variable is 1, equals 6. The coefficient of the first variable, there is no x, so it's 0. The coefficient of y is 2. The coefficient of z is 5, equal -4. The coefficient of x is 2. The coefficient of y is 5. The coefficient of z is -1, 27. So this is a system of equations, and I can put them in matrix notation. It becomes like this. This is the matrix multiplied by a vector x, y, z, which denotes the different variables, and this is equal to 6 minus 4, 27, which is another vector. This is an equation. This is the system of equations displayed here, but now in a very simplified notation. And this is precious when you have a huge amount of equations, a huge amount of variables, a huge amount of things. And why is precious? Because this is what people use in machine learning the whole time, actually. The guys who do machine learning, they have to do these things. They need to know. Otherwise, it's not possible. How do you store information in certain elements? Not only that, some of them, they know tensors, they know advanced tools, etc. But matrices is fundamental everywhere. And even if you don't do machine learning, still, when you manipulate data, you can use matrices. And this shows the equivalence. If you multiply this by this, x plus y plus z, this was the first equation you saw, equal to the number, equal 6, I think, and so on. Now you can solve the equation. This is the matrix notation of this equation. A times x equal b. And then I want to solve x. Now I want to know what is the value of x, y, z. I want to solve this x. If I want to solve x, I multiply from the left by the inverse of a, obtaining the identity here. Is what I do here. I have this equation. I want to solve this. Solve. What do I do? X minus 1a, x equal b. This is the identity. So you obtain x. Done. This is what they display here. Then at the end of the day, I have to calculate the inverse of this matrix in my software. I calculate the inverse of this matrix, and I multiply by this vector, by this column vector, which is a matrix. A vector is a matrix. It's a special case of matrix. It's a matrix with 3 rows, 1 column. And then when I do this operation, I have x. Let's do it explicitly in our software for you to realize how to do it, because I see faces like this confused a little bit. We have the final result is this, right? Let's write the matrices. Matrix A is what? Is 1, 1, 1, 0 to 5, 2, 5 minus 1. B is equal to what? Is 6 minus 4, 27. Then I will use this result. I will calculate the inverse of A first. Let's do it. Let's do it together here. Let's go to my Wolfram something. I will open a new notebook. I will bring it to here. And again, I will go here too. Let me see that I am sharing this thing because okay, it's this one here. Then search matrix operations. Here, this one. Well, first I will calculate inverse, right? So I should have matrix operations again. I want to calculate the inverse of one matrix. Here, inverse. I will copy and paste this case here, and I will change to my case. But I don't like this notation, so I will use the notation of matrix, which is like this. Then let me see the matrix. I want to calculate the inverse of A, 1, 1, 1. The first row, 1, 1, 1. The second row is 0, 2, 5. And the third one is 2, 5, minus 1. Well, actually, why is calculating the trace? I didn't say trace, I say inverse. Yeah, it's inverse, not trace. I don't know why the system copied trace. Probably was copying the previous command, no? The previous order. Then let me delete this. TR is trace. Done. Then I will change here. Evaluation, evaluate cells. Display as matrix. This is the inverse of this original matrix. And I want to multiply this inverse, this result. I will copy, paste here. I want to multiply it by this guy here. Uh, 6 minus 4, 27. It should give me something. This is the result. I solved the three variables. I solved x, y, and z. X is 5, y is 3, z is minus 2. Should be like that. And then let's display the result. Look at the result I obtained here. 5, 3 minus 2, right? Memorize. So I will copy here because you say, no, this guy is cheating. No, I will copy here. Look, x is 5. Y is 3. C is minus 2. And let's see what did they obtain here. 5, 3 minus 2. Exactly what we obtained. Let me share the right screen. Here you are. 5, 3 minus 2. So my software is working well. I am testing it. It's quite good. Of course, you could do it by hand, but nobody wants to do by hand when the matrices are too big. You have to use the tools. No, that's why we have the technology. I think nowadays it seldom happens that people do by hand big operations. When the operations becomes too big, it's not by purpose, it's because we want to avoid errors. humans, we do errors. I try to do by hand most of the operations, but those operations are compact in the sense that tensors, blah blah, we can compactify everything to advanced expressions. But when you deal with huge amount of data or these kind of things, there is no way to do it by hand. There is no way. Simply, there is no way. So this is where you wonder how people in the past did. So this is how to solve systems. There are questions, of course. I will ask you later to solve things, etc. But for the moment, we have to go to break. After the break, we will close this with eigenvalues and eigenvectors. And eigenvalues and eigenvectors is very important. Why is an eigenvalue? Why is an eigenvector? When you have data, let's assume you collected your data somehow, and you correlated the variables somehow, and you have this data like this. It's approximately your line cross like this. So this data is not symmetric with respect to this axis. There is a way to find the axis of symmetry of this data. Axis such that the data you cross around it, around that axis. And those axes is called eigenvectors. Those are called eigenvectors, and they have eigenvalues. Let's assume you have a picture. I think this is the typical example. When you have a picture, I will show you later of, I think it should be here. Let me, oh wait. I'll put here this one. Picture. This is the best example, actually. The picture of this dog. If you distort the picture, the upper side, you will see any vector pointing here. Oh, wait, let it recover. It will recover. Any vector pointing, it will be shifted, no? It will be moved. But this vector doesn't move actually. It maintains the same. This is an eigenvector. The eigenvectors, they don't change the orientation on their transformations because they represent axes of symmetry. And it's important sometimes to locate the axis of symmetry of your data because it tells you something. You can play with the geometry of your data. I will give you an example. Some time ago, I helped some guys, and actually it's published in some books somewhere, to analyze the revenue management in airlines. Yeah, physicists can do that. Then, in that case, it's possible to find an axis of symmetry for the relation price-demand. You can find the eigenvectors. So this is possible. And this axis facilitate the analysis because those are fixed axes. Then you know your data is symmetric and you have some meaning. That vector, this vector itself means something in your research project. It has some special meaning. Maybe it represents some directions, some special prices, some special behavior of the customers, whatever. But that meaning has to be found by you because it's case by case. Every project is different and the interpretations change project by project. So there's no universal way to interpret this because it depends what you are doing. In this case of the picture, of course, it was distorted. It only means that this axis, this is a fixed line. It's a line of no change. Yeah? The pixels, whatever you do it, they remain fixed here in this axis. Yeah. How do you find those vectors? I will explain that in the coming section of the class, the second part of the class. And this will close the part of linear algebra. And then we'll come back to the statistical part next week. So let me stop this thing, stop share, stop